Good day, folks. For those of you who are currently in the session, we will be getting started here in a couple minutes, the top of the hour. We'll just give folks a couple more minutes there to join in to the session. Few housekeeping notes for those of you who are here right now. The session will be recorded. If you had to drop off early or maybe want to share the session's content with a colleague who might not have been able to make it, that will be available for playback at the end of today's presentation. So no worries there. Also, please feel free to make use of the Q&A feature within the platform as we go through today's content. If you had any questions, wanted to discuss maybe some of the relevancy to your application or your work, please feel free to shoot those messages across. We will reserve some time near the end of the session for a formalized Q&A. Okay, so yeah, about another minute, we'll get started here. Okay, so I see a few more people joining in still. I think with that, we'll go ahead and get started here, folks. So welcome and thank you for joining today's webinar. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. Later on in the session, I will be joined by my colleague, Sarah Ackermann, who is our Laboratory Services Manager at Thermal Analysis Labs, who will be taking us through the bulk of today's session. So today, title of our webinar, Sample Observation, a New Dimension in DSC and Thermal Analysis Applications. We'll be going into that in further detail throughout the session here. So just to maybe start things off, just a little bit of background on C-Therm, who we are. Just wanted to quickly introduce for those who may be new or haven't been part of these webinars in the past. So C-Therm, we are experts in thermal conductivity, specifically leading in the industry for transient methods. We are a global reaching company with a distributed network around the globe. At C-Therm, we really focus on simplifying thermal conductivity testing for the materials of tomorrow. That is our core and what we do best. But today's session, of course, is really more focusing on a different material property, specifically looking at DSC and some of those capabilities. And related to this is the Rigaku thermal analysis product line. So C-Therm and Rigaku, we are partnered. We distribute the Rigaku in North America. And today's session will really be going into this aspect of thermal analysis. So again, things like differential scanning calorimetry, simultaneous thermal analysis, and thermomechanical analysis is really the platform suites that Rigaku has to offer. And again, specific to today's topic is the sample observation feature. You can see a picture of this here, just maybe as a little preview for what will be discussed, a really neat novel capability that has been developed by the folks over at Rigaku. And as I mentioned, Sarah will be going into this in further detail here today. So with that being said, I would like to formally introduce Sarah Ackermann, who is, again, our Laboratory Services Manager out of the Thermal Analysis Labs group here at C-Therm. Over a decade of experience with thermal analysis in a range of different applications and material products. With that, I think I'll pass the baton over to you, Sarah. Please feel free. I'm going to stop sharing my slides. Feel free to take over. Thank you very much.
Thanks so much, Arya, for the introduction. I appreciate it. All right, so with that, we can get started. So as Arya was saying, please feel free to drop a question in the Q&A section. We will be having a Q&A session at the end of the webinar. So as a basic outline of what we're going to be talking about, I'll start off by introducing thermal analysis, DSC, STA, and what sample observation is. And then I'll go into the sample observation case studies and do some STA sample observation case studies. And these case studies are ones that I've picked where the sample observation functionality enables the collection of information that you could not understand with DSC or STA alone. And the reason why I picked that is because I want to highlight how this can be used to solve real research problems. So with that said, let's get going. So thermal analysis is a kind of an umbrella term. It refers to a group of techniques that study a physical property or several physical properties of a substance or material as a function of temperature and or time. So we have DSC, which will measure heat flow and temperature difference between a sample and a reference as a function of temperature and time. We also have PMA, which can measure dimensional changes as a function of temperature and time, and also force in the case of PMA. And then over here, we also can do simultaneous thermal analysis, which will study weight and also the weight and this temperature difference between the sample and the reference side as a function of temperature and time. So DSC, what we have in most DSC setups, there are a few specialized techniques out there that have a different sensor setup, but the vast majority of DSCs look on the inside basically like this. You have a sample side and a reference side. The sensor plate is inside of a furnace chamber, which is able to be controlled very precisely to a set temperature. There is a sample thermocouple, which is very close to the sample side. In this case, it's actually right under this little bridge here. That is designed to capture the furnace temperature at the sample location or very close to the sample location. DSC can be programmed in isothermal temperature scanning or temperature modulated ways, depending on the experiment, the apparatus, and what you're actually looking to measure. There are a few limitations of DSC as much as it is a very powerful technique. So one of the biggest ones is that it doesn't show dimension changes or color changes. The other thing is if you have a very low intensity phase change event, and we'll actually see a video of this later on, you can sometimes miss the phase change on a DSC, or it can be so subtle that you might misattribute it to noise or maybe a glass transition or something of that nature. When examining the sample observation video would show that actually that is a phase change. Likewise, it doesn't really show shape changes. So if the sample is contracting with temperature, for example, that wouldn't necessarily be visible on DSC, although the friction caused by sample motion can sometimes show up on DSC, and DSC might not be able to tell the difference between friction from sample motion and a really complicated thermal event occurring. It also doesn't show mass changes. Can't on its own, without additional information, tell the difference between a phase change and a reaction. And it can't distinguish between different types of exotherms and endotherms without additional information. So it's a very powerful technique, but it's except for a few special cases, it's not really a standalone technique. It's more of a technique that you use in partnership with other techniques. So sample observation pairs video, it couples video observation of the sample with either DSC or STA. So what this is going to do in terms of the experiment is it will actually give us visual information about what is occurring with the sample. So we can see on this example plot with the STA, we have a phase change here, shape changes in this straight region. When you compare this temperature video versus this one, you can see that this it looks like something you would attribute to a glass transition, but you can also see some discoloration. So we can see that there's an onset of some degradation there. And if we go up, we can also see that this is about the onset of mass loss. So that also confirms that we're also starting to see some degradation. So this is not a glass transition, but it's the start of the broad exotherm, actually. And as we continue through the still video, we can see the sample get progressively more degraded until finally combustion is complete. So this is a case example of sample observation. So in terms of those limits we discussed previously about DSC, it can partly show the dimensional changes, although you can only quantify those dimensional changes in the case of very, very large ones, and also in 2 dimensions. So it's partly resolved that limitation. It does show color changes. It does show the phase changes. It does show shape changes, and it can tell the difference between phase change and reaction with that color information. And it can also help to distinguish between different types of exotherms and endotherms without added information. It's not perfect in DSC only, but we get a lot more information than we would just with DSC on its own. So most of these case studies are done using the Rigaku DSC Vesta or its next generation equipment, the DSC Vesta 2. Both of these units offer very high sensitivity and performance. We actually have one in our lab here at C-Therm. They have very low noise and a really compact furnace. You can get to from minus 170 all the way up to 725 degrees C using a single furnace, depending on what cooling accessory you pick. It also has a really fast cool down time, which is convenient if you have a lot of samples to get through in a day. And the sample observation temperature range is a little bit more limited. You can go from minus 70 up to 350 degrees C. Below about minus 70, you'll get some frosting issues. And above that temperature point, the thermal strain gets a bit too much for the optics. There is an auto sampler available for the system as well. So the first application note that we'll share is on a molecule called para-azoxyanisole. So it has this structure on the right-hand side of the screen here. And it's a really important molecule in the history of LCD display development. In its classical structure drawing, you can see there's a Zwitter ionic structure. And the presence of that Zwitter ionic structure means that this double bond is actually a bit more free to rotate than it would otherwise be, which is part of what contributes to its liquid crystalline behavior. It's not the only reason liquid crystal stuff can get quite complicated, so I'm not going to go into full details on that, but that's the short version. It's a slightly asymmetric molecule. In this case, it exhibits nematic behavior. So there are 2 different types of liquid crystalline phases, and nematic just happens to be the one that this molecule shows. I won't get into the other one just for time. So in a fully crystalline structure, all of the molecules are ordered both in orientation and position, kind of like in the drawing that I've labeled crystalline. In the case of pneumatic, there is a imperfect order in orientation and somewhat disordered positioning. So you can see these are all oriented about in the same direction, although there might be a little bit of deviation, and there's a bit of disorder in terms of where they're actually positioned. In the liquid phase, it's random. So the differences here is liquid crystalline is a more ordered state than a full liquid, but it's less ordered than purely crystalline. So at this point, I'm going to share the video, which means I need to get rid of my laser pointer. And we'll just watch together on this video of the sample observation. You can see as it goes through, we're going to have the melt, or rather the conversion to the liquid crystalline state and then the melt. My bad, I misspoke. And then as we cool, you can see we have first the transition to a liquid crystalline phase. And then we have two different crystal transitions here. So there's an intermediate crystalline phase and then the final crystalline phase. So without additional visible information, it would be hard to understand why the heating cycle shows really a single peak in that crystal to liquid crystal transition range. We can see that there are probably two overlapped events in this peak here, but it's hard to understand why we have such a large separation on cooling. And in addition, the temperatures are quite different compared with the heating cycle. So this has quite a bit more hysteresis than would be expected in a more classical type of simple phase behavior. So the sample observation video helps to understand materials with these kinds of more complicated phase behaviors. The next application we'll take a look at is looking at polyethylene terephthalate. So polyethylene terephthalate is a semi-crystalline polymer that's used in a variety of applications. Classically, it's used in soft drink bottles, but it's also used in packaging, thermal electrics. It's used as a plastic additive and thermoplastic resins for waterproofing, etc. This is an incomplete list of the places where it is used. But regardless of where it's used, the phase behavior is really critical to designing the process that you're using this material in. So this one's a little bit different. I'm actually going to show two different videos, one at a time. And I need to get rid of my laser pointer again. So the first one, you can see the transition to a rubbery phase, and then the cold crystallization to when it becomes cloudy. In this one, as the glass transition occurs, you can see the onset of the micro-Brownian motion that characterizes the glass glass transition into the rubbery phase. So the micro-Brownian motion is what causes the material to behave in a rubbery way. And this polarized lens enables us to actually see that Brownian motion in the chains of the PET. So it aids with understanding what is actually going on within the material during that glass transition. The next few applications are going to be looking at simultaneous thermal analysis. So a quick review for those who are not familiar with simultaneous thermal analysis. So in simultaneous thermal analysis, we're measuring both mass and either heat flow or temperature difference between the reference and sample sides of the device. So effectively what this is doing is coupling the technique of thermal gravimetry with DSC. And this lets us address a few of the limitations in DSC. Rigaku's STA, their 8122 system, has an interesting horizontal differential STA balance, which lets the balance drift be canceled and limits the effect of buoyancy errors within the system. In addition to that, because it's got a horizontal balance orientation, it's more resistant to vibration caused by gas flows, so it can tolerate a larger amount of gas flowing within the system compared with a vertical or hang down style balance. Comparing DSC versus STA, so the biggest difference is that instead of everything resting on the same plate, in an STA system, typically, if it's TGDTA, we have the sample on its own arm and the reference on its own arm. There are some systems that put them both on the same arm. That has some benefits and limitations. One of the limitations is that because you would have one and then the other, the two samples would not necessarily have the same thermal environment because they might be in different distances from the edge of the furnace. So it makes it more likely that you're going to get baseline drift effects, especially if you're getting a large mass change within the sample side. There are also a few other systems that have a single rod in a vertical orientation, and that's another way of dealing with the same problem, basically. A vertical setup will tend to have a bit more precession, just a circular motion. If you've ever watched someone balance a plate on a stick, it's that sort of wobbly motion that the stick makes, which can affect your baseline quality. So STA addresses the mass change sensitivity that is lacking in DSC. It also partly resolves the ability to tell the difference between a phase change and a reaction, in that you now have sensitivities to reactions that are associated with a mass gain or a mass loss. What it does not have sensitivity to is reactions which are not associated with a mass change or a mass loss. There are some organic reactions, for example, that are not associated with mass change, but the molecule structure itself changes, and STA would not be able to tell the difference between that sort of reaction and a phase change. It also cannot distinguish between different types of exotherms and endotherms in all cases. So you would be able to tell the difference between a phase change and a reaction with mass loss, but you wouldn't necessarily be able to tell the difference between an exotherm caused by a phase change versus an exotherm caused by a self-reaction that does not result in a mass loss. So if a molecule polymerizes without releasing a gaseous byproduct, for example. So when we pair STA with sample observations, we resolve almost all of these limitations, and the one remaining one can be addressed by adding in TMA. So this makes STA a really powerful technique for looking at a material as it undergoes different thermal events and really understanding what those events actually are. So a bit of information on the STA 8122. The maximum temperature range on it is from ambient to 1500 degrees C, and you can do that with a single furnace. And it cools from 1500 degrees C down to 50 degrees C in less than 20 minutes. So it's like the Vesta, it's got a really fast cool down time. You can also get a technique called dynamic PGA, where the heating rate of the furnace is adjusted to control the mass loss or mass gain rate of the material, and an auto sampler is available on it. So our first application that we'll take a look at in for the STA system is looking at polylactic acid. So it's a thermoplastic polymer that's made through in two ways, really. One is just by a simple condensation of lactic acid, which looks kind of like this, only with an OH group off of here. Or you can also have a ring opening of lactide, which is the cyclic dimer of lactic acid. The properties are highly tunable of PLA, just by tuning things like degree of cross-linking and the chain lengths. You can tune its mechanical properties, but that can be kind of a double-sided coin, because since its properties are so tunable, you really need to understand the specific batch and grade of PLA that you're working with, and understand its phase behavior, because you can't necessarily take a book value and use it as what the sample is going to behave like. So if we're looking in this one, at this video, we're going to be watching TGA, TMA, DSC, and DTA all on the same plot with the system. And the TG tells us that no mass loss events are happening within this system. As we play the video forward, we can see a small event is first visible around 61 degrees C. This is visible both on DSC and TMA, but not on DTA, but it was visible on the sample observation. We can also see the exotherm at around 91 degrees. This was not visible on the TG. And then we have the endotherm at about 112 to 114 degrees, which is associated with another dimensional contraction, so it's visible on the TMA. And sample observation lets us see that that's a recrystallization at 112. And we also would notice that the sensitivity to this is greater on the sample observation than DSC, DTA, or even TMA. And finally, of course, we can observe the sample through the melt after the TMA has to stop, because the TMA system has a meltdown protection, so it won't let itself have the sample melt on into it. So we can observe as the sample becomes less viscous as we get further into that liquid phase. and it will begin to contract within itself. The next application note we'll take a look at is a classic TGA standard material. Actually, it's used to validate a lot of TGAs on the market. It's a copper sulfate pentahydrate. So copper sulfate pentahydrate is a material with a really well characterized dehydration. So we know what temperature and how much mass is going to come off of it, which is why it's used to validate a lot of TGAs. But it's also commonly used as an algicide, pesticide, and antifungal. The other thing to note, one of the reasons why people prefer using copper sulfate over some of the other common TGA standards like calcium oxalate, this copper sulfate has these pretty blue crystals, as opposed to some of the other materials which tend to look like a fine white powder, and that can be that can make for some uncomfortable discussions for the installation technicians if they're in an airport, for example. So it's easier to explain a blue powder than a white one. It is related to other copper species with different activities. So copper being a transition metal, it can exist in multiple oxidation states. So it's important to understand what the oxidation state of the copper you're dealing with is. And in addition, the color within the crystal is correlated with the electron density at the cation. So all of these water molecules within the system are coordinating to and hydrogen bonding with, excuse me, with either the copper or the sulfate species, and that is the effect on the electric density within the d orbitals of the copper is what leads to the color changes as we do the dehydration. So moving into the video, oops, wrong button. I need to, there we go. Okay, so I'm gonna start the video now. And as it plays, we can see, pay attention to the little dot. And we will observe, of course, copper sulfate classically loses water in 3 steps. We can see the color change in the first step here. And we can see the color change in the second step as it loses more water and becomes paler. And then the final step with the loss of the last water, of course, if you watch the TGA plot, you'll notice each of these is losing approximately 14% of weight from the original mass. And then the last step is approximately 7% of the original mass's weight. So we're losing 2 water equivalents and 2 water equivalents, and then 1 water equivalent. So the thing that we can see here is that the color does change slightly, which is not the classical color of copper sulfate. So that's information about this material, which would not have been available just on the TGA or the STA for that matter. So moving to the next application note, we're going to look at epoxy resins. Epoxy resins are a class of thermosets that are usually made by a ring opening reaction of an epoxy group. So an epoxy ring is a 3-membered ring with an oxygen bonded to 2 carbons. The strain on that ring because none of the molecules are in their ideal geometry, means that it's usually energetically favorable to open that ring and polymerize, which is why epoxies are used so often in polymerization reactions. They're often used in printed circuit boards, fiberglass composites, and two-part adhesives. And understanding the thermal decomposition of the epoxy thermoset material is a critical property to understand and a critical behavior to understand for safety of whatever device it's being used in. So if it's being used in construction, for example, well, how does the epoxy material burn in the event of a house fire? Or if it's being used in an electronic, how much energy needs to be applied to it before the board will start to combust? Those are important safety considerations to be aware of. So we can watch the epoxy degradation in an STA with sample observation. And on the DTG, which is the derivative of the TG signal, we can see what looks like a noisy event, which might make you think that we were observing a more complicated thermal behavior. But what we can actually see is that this noise on the TG is associated with the physical motion of the sample due to cracking caused by the thermal degradation of the material. So that allows us to more confidently assign this as more of a simple combustion degradation. And, you know, be aware that the TG is just the non-smooth ETG curve is being caused by physical motion of the sample within the sample pan and the sample holder. The other thing to be aware of is that we can see on sample observation, which is not visible as much on the TG signal, and even DSC shows it smooth, but doesn't necessarily show any major peaks, is that the sample continues to degrade even after the mass is mostly stabilized. So over here toward the end of the video, you can see that it is a significantly darker color than even 10 degrees before. So the sample observation is giving some understanding that this material is undergoing some sort of thermal cracking event, and it's becoming more char-like, basically, as we go through this thermal degradation experiment. The next series, or the next application note we'll take a look at is looking at starch-filled foams. A lot of starches are being used for biodegradable insulation types of applications. I've seen them most often in cold chain and construction applications with our clients, but they're being used in other areas as well. Basically anywhere where a biodegradable but thermally insulative material would be advantageous. But in the case of these starch-filled foams, or the foams that are being made out of starches, the combustion behavior of these materials is dependent on the composition, the structure, and any additives that are in the foam material. So it's important to actually study the decomposition, because one thing that we can't do is make the assumption that the starch foam is just going to behave like a powder would or like a block would. Its porosity is going to be different. Its surface area to volume ratio is going to be different. And because of that, its behavior in thermal decomposition in either oxidating or inner atmosphere is going to be different as well. So we need to understand that from a safety perspective. So on this video, we can see that on the TG, as I play through, we'll see firstly, we can observe the mass loss on that first step, and it's not really visible on DTA. But we do also see a small thermal event that is visible both on the sample observation and DTA, but not visible on TG. Then we get to the onset of the combustion. Excuse me. And we see that this peak, which has a very broad, small mass loss, is just a slow combustion. And we can assign that with confidence because we have the sample observation video to show that the combustion is complete. The next one that we're going to take a look at is a glass application. So glasses are a really broad class of materials that are amorphous solids. They can be silicate based. You can have metallics glasses. You can also have ceramic glasses, semiconductor glasses, polymeric glasses. Basically, if there is a material, you can probably make it glassy, although some materials are easier to make glassy than others. Some glasses are metastable, and they're formed through supercooling a fluid. Other glasses are stable at a given temperature range, and they're just a natural behavior of the material. So if you think of silica, silicon dioxide, that's a material that naturally is prone to exhibit glassy behavior, especially if it has some impurities within it. So borosilicate glass is another case where it tends to naturally form glasses, as well as several polymers. We have the glass transition temperatures that I identified previously are where the material is transitioning from a glassy state to the rubbery state. So those are also good examples of a natural glass material, or rather a glass which is an inherent property of the material, I should say. So if we're observing glass melting in a video, what we can see as it heats, we can see the TG, and the sample's appearance changes a bit throughout the TG, and the mass does not change during this video. You can also see as it melts, we have this strong contraction in its cross section. And then in the endothermic peak, the material changes color. And then finally, we get to a complete fusion of the material as it completes the melt. And we can see the large thermal expansion associated with the melt, as well as just spreading of the liquid material due to its loss of surface tension. The next one that we're going to take a look at, I should note, those shape behavior aspects would not have been able, we would not have been able to observe those without sample observation. So it's important to understand that we can observe this thanks to the sample observation, but if we were just looking without sample observation, we would have no idea of how the size and shape of the sample is actually changing as it goes through this thermal event. Looking at PHBH, PHBH is poly 3-hydroxybutyrate co 3-hydroxyhexanoate. So it's a naturally produced biopolymer made through bacterial fermentation. And it's used as a naturally sourced and biodegradable replacement for many plastics that are on the market now, and it's still in development. So we don't see it in applications generally now, but we expect to start seeing it roll onto the market pretty soon, or maybe one of its derivatives. So if we're looking at PHBH decomposition, so this particular application note is the note, along with the para-azoxyanisole one earlier, that may really appreciate the utility of sample observation. So I want you to keep your eye on this little notch here that looks like it could be a glass transition or something of the sort. Watch that spot very carefully as I go ahead and play this video. So to start with, it's not very eventful, as we would expect, since the material is in its glassy state. We can see that that notch was actually the melt transition of the material. And then we see an exotherm, an endotherm followed by an exotherm followed by an endotherm, which is caused by the depolymerization of the material and combustion. And then, of course, as combustion completes, the DSC plot returns to baseline. You can also get an appreciation for just how much more sensitive DSC and sample observation are to residual combustion by observing the DSC behavior here. So the DSC does not go to baseline completely until almost 200 degrees past, when the TG has stopped showing significant mass changes. And we can see that sample observation is a little bit more sensitive still. Sorry, I need to go back a little bit, because we do still observe some color changes within the sample holder due to residual burn-off that is visible on the sample observation, but not visible on either the DTA or the TG. So this really gives you an understanding that the residual combustion continues for a longer time to a higher temperature than than you would necessarily think it does. So that's the last application note. The other thing I will note is the software, which you've seen a lot of screenshots and a lot of videos of in this webinar so far, is called Bulios. It's Rigaku's thermal analysis software, and it can control up to 8 units on the same system. And as you saw in the polylactic acid application, you can make a plot of several different signals all superimposed. So you can correlate your mass change with your DTA in your STA. And then if you have a DSC, you could also run DSC to see if there are any small events that your DTA is missing. And you can also run TMA to see if there are any dimensional changes associated with the events that you're observing. So all of that can be done on the same control and analysis software with Rigaku's system. And that is it for me. So with that, I'm going to turn things back over. And I'll stop sharing my screen. Thanks again, Aria, and thank you all for attending.
Awesome. Thank you, Sarah. All right, folks. So just wrapping things up here. I'm just going to kind of go into a little bit of an outro. So for those who may be interested in maybe some more of the additional content or similar content, we do have a range of webinars as well as different publications available on our website, some on similar topics, others across a range of different applications and material properties. So definitely feel free to give that a look if you want to dig a little deeper there. You know, if you're looking to keep up with maybe some of the upcoming webinars, we do have one scheduled that will be actually at next week, a little bit of a different time, but this will be a C-Therm thermal conductivity focus webinar. And we have some guest speakers from Metrovib and Alteo coming to talk about some of the work being done there. C-Therm is similarly partnered with Metrovib in a way that we are also partnered with Rigaku. And then Alteo has some very interesting data to present on some ATH functional fillers for some thermal conductivity applications. So that'll be June 6th. 9 a.m. Eastern. If you want to keep up to date with everything that we're doing, again, upcoming webinars, different blog pieces, content, give us a follow on LinkedIn. That will be the best place to get the latest updates. And we'll also be present at some conferences in the following month. Two of them here to make note of: the Battery Show Europe. This is held June 18th to 20th in Stuttgart, Germany. We do have a booth. We'll be exhibiting there 6-G58. If you're in the area, please feel free to stop by. And then also a little bit later in the month, June 25th to 27th, we will be at the Adhesives and Bonding Expo in Novi, Michigan. Again, similarly with a booth 736. So definitely feel free to stop by if you are in either area during those times. And with that being said, again, it brings us to the end of our formal webinar event here today. There is a few minutes left on the top of the hour, and at this point, we will open up the Q&A session. So if you are interested, please feel free to stay on the line as we answer some of these questions.